Today's lesson is about magnetism and magnetic fields. So our question for today's lesson is, what is a magnetic force and how do they interact around bar magnets? Our key words for this lesson are magnet, north, south and domain. The first thing that we need to do for the lesson is a knowledge check. So make sure that you answer the questions in your booklet. Pause the video to give yourself enough time to answer the questions before the answers appear. Here are the answers. So for the first question, how many types of electric charge are there? There are 2 types. These types are then positive and negative. In what direction do electric field lines travel? They travel away from positive charges and towards negative charges. And of course that's because they represent how a positive charge would move. The positive charge would be repelled away from a positive charge and it would be attracted towards the negative charge. An electric field is a non-contact force because the electric charges do not have to touch in order for the force to have an effect. The air near a sharp point with a large charge becomes ionized, meaning that it then can conduct charges, whereas before air is an insulator. So normally it wouldn't be able to conduct those charges, but it becomes ionized so that it can. A lightning conductor reduces charge in a cloud by emitting a charge through the air, which reduces the charge in the clouds. So it is then less likely for a random discharge from the cloud, which we see as lightning. The machine used to generate electric charge is the Van de Graaff generator. And 2 like charges repel each other, so they want to move away from each other. Make sure that you give yourself a mark out of 8 and make any corrections that you need to in your answers in a different coloured pen. So, our first question of the lesson is, what is a magnet? So you probably do have a magnet somewhere in your home, possibly on the fridge, but televisions, computers and microwave ovens all operate using magnets. Magnets are made from magnetic materials, so the main examples being iron, nickel and cobalt. Those are the pure metals that are magnetic metals. So they are the only pure metals that can be turned into a permanent magnet. That means that it is not temporary, as some magnets can be. They can temporarily be a magnet, but these pure metals can be turned into a permanent magnet, a long-term magnet. As steel is an alloy that contains a lot of iron, that material can also be made into a magnet. So magnets can also be made out of steel. Generally, we say that a magnet is an object that produces a magnetic field and can attract or repel other magnets. In terms of magnetism then, if a magnet is brought close to some steel paper clips, you've probably seen this before, the paper clips are attracted to the ends of the poles of the magnet. This is the effect that we call magnetism, and it's shown by some materials and electric current. As we've then mentioned before, the materials which exhibit this effect are iron, cobalt and nickel. And we also then see it in steel, because steel is made mostly of iron. This effect can also work the opposite way. So it is not just attraction, it can also be when the magnet repels certain materials as well. So magnetism is just the attraction or the repulsion of certain materials. Bar magnets are a type of permanent magnet. It means that their magnetism is there all the time. It can't be turned on and off. It is there all the time. Bar magnets have two poles. They have a north pole, normally represented with an N, and a south pole, normally represented with an S. So here we have our diagram of a bar magnet, and you can see the north pole on the left side and the south pole on the right side. If permanent magnets are repeatedly knocked, the strength of their magnetic field is reduced, and we're going to talk a lot more about what magnetic fields are. So it's something to be aware of when we're talking about magnetic fields, is that the strength can be changed. And you can also then convert a magnet, take away its magnetism, and we call that demagnetization. We can make a simple compass, and you can try this at home if you wish to, by just placing a piece of string around a bar magnet and just hanging it from somewhere, so possibly a doorway, or you could just hold it up. And because of the way that magnets point, when it settles, it will point to the north-south direction. Okay, and this magnet then becomes a simple compass. So you can then tell which way is the north-south direction. So you can then tell which way is north and then which way is south. And obviously I've put then down below resources then that you can have a look at to help you with this. Now we are going to look at what we call the single touch or the stroking method. I believe that in your booklets it's called the stroking method. So an object can be temporarily magnetized by stroking it many times in one direction with one pole of a bar magnet. So it could be a steel or iron nail that you do this with. There are lots of videos showing how it's done, but I've included then a link that you can just copy, or you can just type into YouTube the title. But we've got a diagram underneath, and this is in your booklet, of the process that happens. So you are doing a motion, and it's showing the motion that you can do in order to then produce temporary magnetization. What I want you to do when you are looking at this video is imagining the number of paper clips that the magnet would be holding after a certain amount of time, and the video should help with this answer. So what you need to be doing once you've watched the video is you need to be filling in this table to say how many paper clips you think that the magnet would be holding after a certain amount of time. Here I have some example answers. Obviously if you have different numbers then that's perfectly fine, but the main thing is that as the time increases, then the number of paper clips that the temporary magnet can hold should decrease. So as long as your numbers decrease, then that's the right idea. This is because as the time goes by, the temporary magnetism wears off from the temporary magnet. So less paper clips are then attracted to that temporary magnet. Make sure that you amend your answers if you need to. We will now look at repulsion and attraction, and this idea should be familiar to you because we've talked about it in terms of electric charges attracting or repelling. When we have a magnet, we have a north pole and a south pole. If we put two north poles or two south poles close to each other, they will force each other apart. We call that repelling. So much like electric charges repel, like poles on magnets then also repel. And as the same with electric charges, opposite poles, so unlike poles, attract each other. So that means they will go towards each other. So as I've said before, we will talk about magnetic fields. You can see on the diagram on the right the images of the magnetic fields and what they look like when the magnets are either repelling or attracting. I would like you to replicate the diagram on the left in your notes page on page 13. So turn to page 13, go onto the notes page and replicate the diagrams with the fields, so showing repulsion and then attraction. Make sure that you include the arrows for the field lines as well. Use this idea, so the fact that like poles repel and opposite poles attract, to fill in your table. So for poles it should be north or south, and you should then say whether they would attract or repel each other. You need to make sure that you include all three scenarios, so both a north pole and a north pole, a south pole and a south pole, and a north pole and a south pole. You need to make a note of them whether they would attract or repel each other. So this is how your table should look. So for each scenario you should either write that they repel or that they attract. So remember that like poles repel, so north and north pole repel, south pole and south pole also repel, north pole and south pole will attract because they are opposite poles. Make sure that you mark your work and do any corrections that need to be done. Now we will look at magnetism in a bit more detail in terms of how materials become magnetized. So, materials like iron and steel are attracted to magnets because they themselves become magnetized. So for example then, in iron atoms, electrons in the atoms spin around, causing a magnetic effect. This means that each atom behaves like a tiny magnet itself. So we call then these atoms inside the iron domains. In an unmagnetized piece of iron, the domains point in random directions. So you can see the diagram below, that's blue. That shows then the domains. The domains are represented by the arrows and they are pointing in all random directions. This means that the magnetic effect is cancelled out. So when the electrons are spinning around, that effect is cancelled out. That then means that the material, the piece of iron, is unmagnetized. So it's not magnetic. If the domains are turned so that they mostly point in the same direction, the piece of iron becomes magnetized. So it starts to become magnetic. And you can see then in the diagram below in green, all the arrows, the domains, are pointing in the same direction. Because all of the arrows are pointing in the same direction in the picture, it shows that it's a strong magnet, it's strongly magnetized. And that's because all of the domains are pointing in the same direction. I have then included a link and the title and details then of a video to explore further this idea of magnetic domains. So make sure that you check out that video. I found it very helpful in terms of being able to understand how magnetic domains work. Now we will move on to magnetic fields. So a magnet has a magnetic field. It is a region in which a magnet's force works. So you hopefully recognise the idea of fields from electric fields. It's a very similar thing because it's an area in which a force works. So for a magnetic field, it's where the magnet's force works. You can't see the magnetic field normally, but it's surrounding the magnet. If another magnet is moved into the magnetic field, then the force then acts on it. And the force again is a non-contact force because the magnets do not have to touch each other. So magnetic fields and electric fields are very similar. They're both non-contact forces. And they're both regions where a force works, and that force is a non-contact force. As well as these other similarities, magnetic fields are also vector quantities. So remember that electric fields are vector quantities. So are magnetic fields. Even though the magnetic field is invisible, we can do things in order to see what it looks like. So for example, you can see in the diagram that they have used iron filings around a bar magnet to be able to see the magnetic field lines, the way the magnetic field goes. And then there is a clearer diagram above that showing the field lines around the bar magnet. This diagram is really good because it shows the direction in which the field lines are travelling. Notice that the field lines are travelling from north to south. So much like electric field lines move from positive to negative, magnetic field lines move from north to south. So, with this idea in mind then, you need to be drawing the field lines around a bar magnet. For the part above, so in your booklets, the first bar magnet diagram, you need to be trying to replicate the top left picture, and that is showing the iron filings around a bar magnet. So you don't have to worry about doing full lines or the arrows, it is just the iron filings. Try and just replicate it as best as you can. For the one below, then you need to try and replicate the picture on the bottom left, which is then showing the field lines, so they are full lines. You need to make sure that you get the shape right, and then you also need to make sure that you include the arrows to show which way the field lines are going. So I've included then some circles to help you be aware of what you're doing. So for the top one, you need to replicate the top diagram. For the bottom one, you need to replicate the bottom diagram. Last of all then, we need to make sure that we understand the ideas that we have spoken about today. So, make sure that you complete the knowledge check. Pause the video so that you have enough time to answer all 8 questions before the answers appear. Here are the answers, so make sure that you mark your answers with a different coloured pen, make any corrections that you need to, and give yourself a mark out of 8. So for the first question, the 3 magnetic materials, for this question it is asking for the pure metals that we know are magnetic, and those 3 metals are iron, nickel or cobalt. Steel is an alloy, so technically it's not just a metal, because it is more than one element. Steel is also magnetic because it is made mostly of iron, and iron is magnetic. A magnet has 2 poles, these are south and north. 2 north poles brought together would repel because they are like poles. Similarly then, 2 south poles brought together would also repel because they are also like poles. But a North Pole and a South Pole brought together would attract, because they are unlike poles, they are opposite poles, so they would attract. Magnetic field lines always travel from North Pole to South Pole, so you should have those arrows on your diagram of magnetic field lines showing that the field lines go from North Pole to South Pole. And then with our simple compass, the direction that a magnet will settle if it's free to rotate is the north-south direction. Make sure that you highlight your keywords in your booklet then, and we will just go through these before the end of the lesson. So a magnet is an object that gives off a magnetic field. North is a pole of a magnet. It's the end of a magnet that is attracted to the Earth's magnetic north, which is why when a magnet settles, it faces north-south. So the North Pole on the magnet should be facing Earth's magnetic north. The South Pole then is the end of a magnet attracted to the Earth's magnetic south. So again, when a magnet settles and it faces the direction of north-south, the South Pole of the magnet should be facing towards Earth's magnetic south. And lastly, a domain is a region within a magnetic material in which the magnetization is in the same direction. So remember that domains are atoms within the magnetic material, and if they are all facing the same direction, then the material is magnetized. That is now the end of the lesson. Thank you.